All right. And got it. Okay, very good. Yeah, my name is Randy Peacock. I'm the ASME Piedmont Carolina chair this year, and I'd like to welcome everybody to our joint meeting with ANS. We, through the years, have tried to get together with ANS at least once a year and do a joint meeting, and a lot of times it's been some of our best meetings. And I think certainly for us this year, this is going to be one of our top meetings for sure. One thing going forward is that you know, we're going to try to pursue joint meetings more the rule than the exception at ASME, because I think not only does it allow us to network with others, but also gives a larger audience, which is a nice courtesy to the speakers and so forth. So anyway, on behalf of ASME, ANS, the NC State Department of Mechanical Engineering and their student section, and NC State Department of Nuclear Engineering and their student section, we again would like to welcome you. And so I'm going to go ahead and turn it over to ANS. Is Ryan on the Zoom meeting?
Yeah, I'm here. I think I'm one of the Konstantin Ivanovs, but I'm not smart enough to figure out how to change that.
I'll change it for you.
Very good.
Yeah, so I just turned my video on. Yeah, I appreciate NC State and the other chapter as helping us support this. This is another big meeting for us as well, one of the largest that we've had, and I'm hoping that we can get together in person sometime soon. I'll give a wrap up at the end, but just for those of you that aren't that familiar with ANS, we are part of the American Nuclear Society, a national chapter. It's Piedmont, just like ASME. Steve, I think, is maybe on here somewhere. Steve was the chapter president before me, and now he actually is going on to be the national president. So we will be graced by his presence here in this meeting, maybe if he joins in. So thank you, and I'll turn it back over. Thanks.
Okay, very good. Thank you. And at this point in time, we'd like to turn it over to Steve Ray. Steve is the one who really brought us all together and helped make this meeting a reality. So Steve, if you would please take it from here.
Thank you, Randy. And I am very excited by the attendance for this meeting tonight. Would like everybody to understand what really inspired it. This was inspired by some exciting news that came out in March of this year. The Department of Energy made announcements of contracts that were agreed to between themselves and X-Energy out of Rockdale, Maryland, and TerraPower out of Washington. Both of these companies now have contracts from the DOE to build full-scale commercial small modular reactor projects that are intended to go fully operational by 2027. That was exciting on its own merits, but then we learned that part of the team for those two teams, part of those two teams is a role being played by NC State's Nuclear Department of Engineering. There are two separate teams formed within NC State's Nuclear Engineering Department, one to work with TerraPower and the other to work with X-Energy. These two teams will be involved with the licensing process for those two advanced small modular reactor designs. This is an important role in those projects. And so that was the inspiration for trying to set this up. And so I'm very glad to see, Randy, your leadership pulling this together to make it happen. Thank you. I'm here to also introduce the next person that you need to know, Ms. Lisa Marshall. Lisa's been with the Nuclear Engineering Department at State for about 20 years this October. And she's had a role of Director of Engagement, Retention, and basically, I think what I should say for those of us who aren't involved with closely with the university is she's really helping grow the Nuclear Engineering Department. She's got a leadership role that way, reaching out to communities to get the best students that NC State can get into the engineering department, and working with those students as they grow and working them into a master's degree and doctor programs. She's also been a past board member of the American Nuclear Society. So she's been in this industry for 20 years and been an important leader at the NC State Nuclear Engineering Department. And she's worked behind the scenes supporting Randy and putting this together. So we want to thank her, and I want to turn it over to her.
Thank you, Steve. Thank you, Randy. Thank you, Ryan. I started when I was 10 or so in the department. That's the new story that I'm giving. I am very pleased to see some of you again, and then to meet the acquaintance of others. I have the pleasure of introducing our speaker. When the flyers went out, it was going to be our department head, Dr. Kostadin Ivanov. However, he sends his regrets. He's on travel, and you get the even better than Kostadin. Now, you all can't tell him that, right? You're having Dr. Mohamed Bourham, and I just wanted to read a little bit about him. Dr. Bourham is the Alumni Distinguished Graduate Professor of Nuclear Engineering. He's also the director of the College of Engineering Masters of Engineering program, as well as an adjunct professor of biomedical engineering here at NC State. His research lies in plasma matter interaction, plasma propulsion and thrusters, fusion engineering, particle accelerators and electron beam irradiation systems, X-ray sources for medical and screening imaging, shielding and radiation attenuation studies, nuclear and mixed waste disposal, and most recently on dry cast and high-level waste packaging studies. And an experimental and computational nuclear engineer. He is a member of several professional organizations, including the American Association for the Advancement of Science, Institute of Electrical and Electronics Engineers, the American Society of Engineering Education, of course, the American Nuclear Society and the American Physical Society, and he's a life member of the U.S. Naval Institute, the National Defense Industrial Association, and Sigma Psi. A wonderful mentor to students, faculty, and staff. I give to you, Dr. Bourham.
Well, thank you. I am really, don't know what to say. Thank you, Lisa. This is really amazing. Thank you so much. And I'm glad to see you all. And I'm ready to do a presentation about our department and what we have. And here we start with an overview of, the advanced reactor research at NC State University. This is on behalf of Kostadin Ivanov, our department head, and myself as well. Usually I am his deputy, so we work together, and I will go slowly in some slides and fast on other slides. So next, please. So here, we introduce the state of North Carolina. You can see the evolution of the number of faculty between 2015 to 2019, from 16 to 22. But I'll give myself, an opportunity to go back to 2008 and 2007. 2007, I was the interim department head, and I had only 8 faculty. And, negotiating with the College of Engineering, I negotiated for 3 positions, so they gave me 3 positions, then negotiated for 1 more position to be a permanent department head, because I didn't want it to be a permanent department head. So the number increased from 8 to 12. And then, the fellow, Yusri, ASME, became the department head, and he worked to increase the numbers, and then Kostadin worked hard to increase the numbers. So what you see is actually what we are right now. The pictures of the faculty you are seeing here, and they are actually from top to bottom in alphabetical order. And we are celebrating our 70th anniversary at NC State. The 70th anniversary is when the nuclear engineering program was announced at NC State inside of the College of Sciences in the physics. But 10 years later, it was a standalone, and so we are celebrating the 60th anniversary. Important for us to also say something about our department, because our graduate program is sustaining the rank number 3 over all the entire nuclear engineering departments nationwide. And we are really working hard and maybe to move up to number 2 and the number 1. And we are also number 1 ranked by the college reviews for the Master of Nuclear Engineering, which is a distance education program. We have joint distance education program with Bettis Reactor Engineering School. It is just started as we arrange it together how to make this program to happen. We have our distance education component for the PhD. It's in process and will soon be available. We have 23 tenured and tenure track faculty plus research professors. The enrollment, 129 in the graduate program, 91 of them are PhDs, and 111 undergraduate students. Of our faculty, we have 4 in joint faculty appointments with Idaho National Lab and the Oak Ridge National Lab, and so on. 4 of our faculty are distinguished and endowed professorship, and the 2 are university faculty scholars. I will add here that 3 of our faculty are also members of the Academy of Outstanding Teachers. Our PhD program is actually, is moving well, and we are graduating very good number of PhDs. I'm seeing Ishita here, for example. Next, please. So our recent development, we are members of the 2 awarded U.S. Advanced Reactor Development Program. It was just mentioned, we just heard about it, that we have 2 teams with X Energy and TerraPower and the /GE Hitachi teams. This partnership is very strong, and it is also a good support that comes from Department of Energy. We have also partnership in the Department of Energy for a center for low temperature plasma for interaction with complex interfaces. We have partnership also in 11 university for also energy funded nuclear science and security consortium. We are constructing fission gas loop, that's for our reactor, hot cell facility also, and ultra cold neutron source, which is a basic physics in which the ultra cold neutron source is where you have the speed of the neutrons within 5 or 6 meters per second. We are developing, undergraduate concentration in plasma science. This will be new, and we are also developing a graduate certificate. We already developed a graduate certificate in health physics. It's in place. And we will also, develop and complete a graduate concentration in plasma science and engineering and nuclear materials. These are coming new and will be soon available. The department is in the process of renovation. And the reason for this is because, if we go back a year ago, we had the Castle as a consortium, we have the CNEC as a consortium, and there was no space in our department, so they were actually occupying space on Centennial campus. As a new building was built and all other occupants in our building moved out, we acquired the space and we are reorganizing, and we brought all of our people from Castle and from CNEC to be back to our building, which is the Burlington Nuclear Engineering Building. Next, please. Here you can see that research. What we have. We classified ourselves as major research areas as 4 areas: reactor systems engineering, radiation interactions and detection, plasma science and engineering, nuclear fuel and materials. But of course, we have cross-cutting research areas that will be, of course, components of the above. Nuclear reactor program is a program by itself, nuclear security and non-proliferation, nuclear waste management, and modeling and the simulation, plus healthy physics. All of these are components that actually characterize the research that goes into our department. Research consortia and the centers and the groups, we just said that the reactor program is the University of North Carolina Board of Governors Nuclear Research Reactor Center. The Center for Low Temperature Plasma we just mentioned, Center for Critical Infrastructure, and the facilities. This is, new. We have the consortium from the nuclear power. This is what we call it the post, the post situation of the former castle. So as castle, ended its term, so now we turn into the consortium of nuclear power. We have also, our INL National University Consortium, very famous, and many other universities are also involved. And we have the International CTF Users Group. The CTF is actually a group that use the, the copra for the thermal hydraulics. We have 15 research groups and, laboratories. And of course, we have, a very good and strong high performance computing cluster. To the corner up, you can see that, the needs and the spending for the sources. And you can see that our sources are actually pretty good. Each year, we will get a good amount of the awards from NAUP, Department of Energy. For example, just yesterday, it was announced, and we have 4 new research and development awards, and the 2 new infrastructure awards. And our faculty, some of them are also involved with some other universities as lead universities. But for our university here, we have the lead on 6, 4 plus 2. Next, please. This is our nuclear reactor program, which is named as the UNSC Board of Governors Center. And, it's operational. And, the director is Dr. Hawari. And, it has 30 operating and technical staff. Many of them are actually students. Some of them will get the license and will be also reactor operators. And it has an average annual spending $3 to $4 million. The reactor went critical in 1972. It is 1 megawatt power, open pool reactor, and it is operated to 2 megawatt, and it's under the license with NRC. Once approved, it will be operational with 2 megawatt. And it's a light water moderator. And it's actually very famous for the blue glow, and many of the visitors just come to enjoy seeing the glow. Utilization is about 10,000 users, user hours annually. This is because it is, full of facilities, and it is contracted to so many companies, national labs, and other universities to do research and to do irradiation testing. Some, for example, like NSF, for example, and many of others. The mission of this reactor and the reactor program can be characterized in 3 categories: the education and the training, the research and the discovery, the outreach, extension, and the service. Education and the training, it's open to all of our students, our faculty, as well as our colleagues from anywhere else. The research and the discovery, it's multidisciplinary because it is equipped and very nicely equipped with many of the facilities that will be shown in the next slide. And the outreach, of course, is a component and an important part, and usually the outreach goes to Lisa Marshall, as she is the director of the outreach. So here in the nuclear reactor program, we can see that the major materials examination and irradiation capabilities, neutron powder diffractometer, neutron imaging facility, intense positron beam, and all of these are doing great for materials characterization. Fuel testing and efficient gas release loop. This is new. This is new, and it is supported by the Department of Energy. Ultra cold neutron source. This is a long-term physics of the neutrons in basic science, and it is still under the construction, so hopefully will be operational soon. Neutron activation analysis for elemental forensics. We do this, and we actually provide such testing for many companies as well. And the hot cell facility, it's new also here. The in-pool irradiation testing facilities available. Also, we have many contracts with industry, and this industry brings a lot of income to the reactor program. The national and the instrumental partnership partners with DOE, INL, of course, NSCUF, because it is classified as one of the national, science user facilities. It's a partner with, many of the national labs and Internet Reactor Laboratory. It's a partner with NSF, member of International Group of Research Reactors, member of NNSA, and so on. You can, really name it. The reactor is a unique facility, and it has its international reputation. Next, please. The post-CNAC and the plasma activities. CNAC was one of the consortium that was for, supported by NNSA, and as the CNAC, completed its, 6 year, $25 million for 6 years, and as it was completed, then by September 30 of 2020, CNAC was dissolved. Because of this, so NC State University established a joint faculty appointment agreement for Dr. John Mattingly, his picture on the top, with the Savannah River National Lab, and this enables to expand our engineering and the post-CNAC activity. In the spring of 2020, the National Lab engaged with the Nuclear Engineering Department in the 3 pre-proposals, and of which, received a green light. So at least we know that one project is ongoing. There is also, one of our colleagues, Dr. Kawami, he's a nuclear material scientist, and he is involved in a 25 million grant funded by the Department of Energy, National Nuclear Security Administration, and and this actually consists of 11 universities and the 5 national laboratories. So the 25 million is a very big umbrella, and he is partner into it. We also have faculty working on interesting modeling problems, and in medical and the medical applications. Dr. Steve Shannon is working on some medical applications using plasma techniques. Me too, I do something, very similar. We have also Dr. Katerina Stapelman, and she is working on plasma for life sciences. You know, a very nice and unique activity in our department established by her. And so this actually looking into a new generation in employing the plasma technique into what we call medicine and agriculture. Next, please. So the capabilities in modeling and simulation, strong capabilities. You can see here at the bottom, the pictures of those who are heavily involved in modeling. You can see, you know, from left to right, Scott Palmitag, Maria Avramova, Konstantin Ivanov, Jason Hoff, and Igor Bolotnov, and Namdin. You know, the Castle activity has ended in November 30th of 2020. Then we moved into what we call it the post-Castle and the development of the consortium, a new consortium. So the examples here, Scott Palmitag is also on a joint faculty appointment with Oak Ridge National Laboratory. And he is doing, you know, modular reactor, you know, and modeling. We have also Scott, you know, and Dr. Maria Avramova. They are also involved with the BWR, with, you know, Department of Energy. Vera users group, that includes also the use of the Cobra TF, and it's also, again, Maria Avramova. There is an award of project benchmark evaluation, and that's, you know, a benchmark that was awarded to Maria and Konstantin in cooperation with Idaho National Laboratory. We have also strong collaboration with Oak Ridge National Lab on development of simulation capabilities and validation. There is also the work on the metal fast reactors and, you know, on verification and validation and the quantification. We have also the participation in the Department of Energy NEP IRP, Integrated Research Project. And this one does include, you know, our faculty, Namdin, Igor Bolotonov. And, you know, here also we have the projects with Benjamin Beeler. He is one of our new faculty and on a joint faculty appointment with Idaho National Laboratory. Next, please. So the Consortium for Nuclear Power is an evolution coming as a post-Castle. This one has major goals. It needs, you know, increase the research output, attract a new source for funding, development and collaboration, new and novel areas of research, become, you know, it's like also a participation with industry, with national labs, with universities, and so all can come together and be partners in this consortium. For example, industry has the Industrial Advisory Board is Southern Company, you know, Rolls-Royce, Global Nuclear Fuel from Japan, Framatome, all right, X-Energy. You see all of these. Westinghouse is a very strong supporter to us. And then we can see that university members, Penn State, 2 universities from United Kingdom, 1 from Turkey, and University of Florida. All of these are actually university members. Next, please. So other research areas actually leads in nuclear engineering applications, data analytic coupled with, you know, artificial intelligence, you know, the 2 related projects with DOE led by NC State University, Namdin, right, and Maria Avramova, Igor Bolotnov. It's involved industry and the national labs. This is development and applications of the data-driven, you know, methodology. It is also, you know, looking into validation of risk-informed safety margin characterization modes. Development of nearly autonomous management and the control systems for advanced reactors. This is an ARPA-E type, grant. It's a 3-year measure with Brookhaven National Laboratory using, machine learning techniques. Machine learning is becoming important in so many activities. And in code validation, and Maria is very heavily involved into this. Another ARPA-E project led by X Energy, it was mentioned, was awarded in 2020. And, it has also Maria as the PI and Jason Ho and as a co-PI. We have also one of our young faculty, Mihei Diakonisa, who's one of our new faculty, also partner in this project. So, other awards and research projects, partners with ANS-ASME. We love ANS-ASME, and I think that they like us as well. Multiple awards in the EUP, NSF, we get, I just mentioned that we just this year obtained 4, regular grants and the 2 infrastructure, multi-awards project in plasma science and engineering with government and NIH as well. And recently, one of the recent in plasma science applications is an NAUP for one of our new faculty, Alex Bataler, and our faculty, Katarina Stapelman, who is leading the plasma for life science research. Next, please. So international cooperation activities heavily involved. And we have to give the credit first to Kostadin, who established all of the strong collaboration, he and Maria Avramova. And they established all of the good relations with the International Atomic Energy Agency, for example. Also the many bilateral agreements with South Africa, also in Germany and Switzerland, also the Nuclear Energy Agency. All of these are very strong activities internationally, and we are very heavily involved in the international activities, and we hope that we can also spread this to other territories. Maybe we can extend it to maybe Japan and some other countries. Next, please. So in conclusion, what's about NSC State Nuclear Engineering? It continues to grow strategically and diversifies. We have well established as well as nationally and internationally recognized. This is important to say. Collaboration and partnership with industry, national labs, government agencies, and other universities, from all over the nation, including universities from overseas, because I just mentioned that we also collaborate with South Africa. But also, we also are recipients of students from, other, international, students in our PhD program. And this is actually one of the most important assets to us. Strong engagement to tackle grand challenges of nuclear sciences and engineering. We are developing our 5-year strategic plan in line with the university and the College of Engineering plans. So we have the College of Engineering plan, and we have the university as a big umbrella, and we line up our 5-year strategic plan along the same, level. Looking at developing and expanding our experimental facilities, that's why we submit for infrastructure, so we get more of experimental facilities and instrumentation. And this year, we are granted 2 new infrastructures from NAUP. And this is for advanced reactor technologies as well. This is our department, Department of Nuclear Engineering, NC State. And, thank you so much for, listening.
Thank you, Mohamed. I'm going to take a bit of liberty and move the panel to right after, so that then you can hear about the advanced reactor research work that Ishita Trivedi just finished. If she would give a bit of information about her work, and then we all will sit on a panel that you can pepper us with a set of questions, and then leaving enough time towards the end to play the video kind of taking you through our facility as well. So let me tell you a little bit about Ishita. Dr. Ishita Trivedi works as a computational scientist at Idaho National Laboratory. She received her PhD in nuclear engineering at NC State with a focus on advanced reactor modeling and simulation. Ishita also has a Master's of Science and a Bachelor of Science in Nuclear Engineering, one from NC State and the other from Penn State. While at NC State, she received the Graduate Merit Award, the Doctoral Fellowship, and the 2020 Doctoral Scholar of the Year Award. She is active in the American Nuclear Society, where she's on the executive committee for the Young Members Group and the Education, Training, and Workforce Development Division. She is also on the sponsorship committee for Pfizer 2022 and was the immediate past chair of the American Nuclear Society 2021 Virtual Student Conference. Ishita serves as the chair of the advisory board of Generation Atomic, and outside work, she enjoys exploring museums, running, and learning to cook. So we're going to hear from her, kind of tell you a little bit about her work, and then we'll open it up for questions for Ishita, Mohamed, and myself.
Thank you so much, Lisa. Good afternoon, everybody. As Lisa mentioned, my name is Ishita Trivedi. I'm a computational scientist at Idaho National Lab. I actually started just a month ago. I finished a month at my job. I finished my PhD degree, took a week break, and then just jumped right into it. For my PhD, I worked with Dr. Konstantin Ivanov and Dr. Jason Ho. And my research, the dissertation title was Uncertainty Quantification and Propagation Methods for Safety Analysis of Lead-Cooled Fast Reactors. Essentially, I did a lot of modeling and simulation and tried to understand uncertainties and coming from nuclear data and how they propagate through lead-cooled fast reactors and impact core safety. I was also involved quite a bit in on the uncertainty side in the benchmark for sodium-cooled fast reactor that Dr. Bourham mentioned in his presentation just a few minutes ago. And then I also did some work with Argonne National Lab throughout my career on various designs, doing internships and such. And recently got involved with thermal propulsion reactors at INL. I still focus on modeling and simulation. I work on the NASA and BWXT projects, the joint projects on nuclear thermal propulsion reactors. As I said, I just started a month ago, so I haven't really dug that deep into it. I'm still on surface level, but overall, it's really exciting, and I really enjoy what I'm doing. I keep telling my parents that every time I turn on my laptop, it feels like I'm turning on an episode of Star Trek, because I read these statements that say intergalactic, blah, blah, blah. These are the things you only hear in TV shows. So it really is self-motivating, and I really enjoy what I do. Within the nuclear community itself, I've been part of ANS for so long, mostly because I believe in the cause so much. I truly believe that innovation is the key to scientific progress. And that's also why I continue to look for projects. In Gen 4, got involved with liquid metal cooled reactors and NTP reactors and so on. I think that summarizes what I do. I got involved with Gen A because I believe that there really is no substitute for zero emission energy sources other than nuclear. Whether the community truly understands it today or not, eventually everybody will, and it's our job to guide them there. So wherever I can get involved, I try to get involved and just provide my contribution to the community. I think that covers what I do and why I do it, Lisa.
Thank you. So we're going to open up to pepper the panelists with questions. What questions do you have for us? You can raise your hand within Zoom, and that is, I always forget where it is. I always have to go looking for it.
It's under reactions.
Thank you. Under reactions, or
Lisa, I see Richard Rodano has his hand raised.
The old-fashioned hand. Richard? Yeah. Or you can chat, put it in chat too.
Thank you, Lisa. I still raise my hand because of the vintage of when I went to school. I'd like any of the panelists who care to address this. I try to keep track of the evolution of new reactor technologies. What do you think of the lifter technology as a potential new source for commercializing nuclear power?
Mohamed?
I would say that everything is valid. Of course, you know, I haven't heard recently any news, but you know, usually news can just show up anytime. But I haven't heard anything new.
So there's a question from Sven. What fission gases are being investigated in the fission gas release loop on the nuclear, our pulsar reactor?
I think the xenon is one, all right, because you know, I was involved in this for quite long time ago. Me and Dr. Hawari, you know, it's xenon, and even we made you know, a system to detect the release of the fission gases, and it was specifically xenon. Maybe you know, krypton, but the xenon is essentially yes.
Randy, I thought I saw your hand up, or your virtual hand up.
Okay, well, I was trying to type a in the chat too, but it's probably easier for me just to describe it. Has NCSU ever worked with the University of Rochester Laboratory for Laser Energetics?
I don't think so. I don't think so. Mohamed, you have a longer memory than me.
Well, you know, I don't really recall work with University of Rochester. I don't recall. Other universities that, you know, collaborated with us, like University of Florida, you know, Penn State, you know, Texas A&M, you know, with some limitations, MIT, Michigan, but University of Rochester, no, I don't recall.
Okay. The reason I ask is that my son just went to work there. I'd never heard of it, but he's been telling me all about it. And it's fairly fascinating with the work that they're doing with laser fusion. So it just got my curiosity going.
Fusion?
Yes.
Well, there is an incredible work on fusion that's going on, you know, locally and internationally. And, you know, I have been involved in fusion research, me and John Gillian, for quite long time, okay. You know, over maybe 25 years and more.
Wow.
And our recent thing, it was actually work on the fusion materials in my student 2.5 years ago, was doing the research and the shuttling between Oak Ridge National Lab, our facilities here, and you know, and the fusion facility in La Jolla that belongs to General Atomics. And after completing his dissertation work, there was an announcement from the international facility, ITER, for you know, 5 postdoctoral fellows from among the entire world, one from each country. And my student was chosen as the one from United States, and he spent 2 years there. He just came back, and he is now employed by Sandia National Lab.
Oh, okay, very good.
Yes, because
There's a lot
Sandia
going on.
National Lab, they have a major facility that's, a major plasma focus facility. And so he is joining there.
There's a question from John Cyphers. What new research or industry projects will the 2 megawatt upgrade to the pulse star allow us to do? More neutrons. We're all excited.
Yeah. Well, and also you can go into, for example, different ranges of irradiation, in pool irradiation when you have, high power. So this will be very good for, materials people.
Excellent. Okay. I did that one. Steve, do you want to ask a question as I scroll up?
Sure, thanks. Yeah, I've been on Teams today and I'm not bilingual, so I can't get adjusted to the Zoom here. My apologies. So I couldn't figure out how to raise my virtual hand, but I got the impression, I mean, you described, the panel described an impressive amount of research that's going on. And so let me ask a leading question. Is there a lot of money and resources available for nuclear research these days? It kind of sounds like there is.
Actually, yes. Yes, there is. Because of course, the annual cycle for the Department of Energy, NEUP, which is the nuclear, engineering, it's actually a program that has been ongoing for the past maybe more than 15 years now, and each year we get at least 4 or 5. Each project is capped to about 800,000 for 3 years. So you can see that the amount of money that comes from Department of Energy in support for the research in the department is quite big. This is in addition, of course, to NSF, all right, or some other resources like NSAA. And because we had previously the 2 consortia, the Castle and the CNEC, so each one was actually multi-million dollars. One of the things is that, I have to say that in open houses, in engineering open houses, when the students come to explore and they have their families, so they may ask someone of the presenters, do you have scholarships? So they said, oh, if you want the scholarships, you have to go to nuclear. Which means that it is the department that has the largest income in research funds in the university. It is true. It is true.
Another question from Sven. Is the attempt to recover the xenon separated from the krypton, maybe with metal organic frameworks?
Well, because this was some long time ago, but I tell you something, because we developed a system that's actually, we even filed an invention disclosure for it, where it actually gets the fission gases and goes into a chamber that the chamber makes the separation the xenon and the krypton, and then you can determine the fission release. But that was some long time ago, and I'm not quite sure now if this is the same thing or there is another technique employed with the reactor people.
Okay. Another question for the recently graduated seniors that weren't going on to graduate studies. How did they find the job market? And then how do you feel, how do you have a feel for how many incoming students are interested in nuclear engineering? So our our graduating class was smaller this year, and I would say about 40% of them are going on to graduate school. We have an accelerated master's program that we fund. So we are double counting some courses, and then they have 1 year to finish that master's. And there's the added incentive that tuition and fees are covered by us, and then they can work with one of 24, soon to be 25 research faculty members, right? So, and then of the others, there are 2 that started looking late. So one literally started right after he graduated. Mom and dad, I'm sure, are not too happy about that. And another who started in the fall semester, but I think he's burnt out. I think he wants to travel, but the little thing called a pandemic is altering that opportunity. And then the others, some have gone on to shipbuilding, or the shipyard, so working with Newport News and or NAVSE. And then we had some that were commissioned officers upon completion of the undergraduate degree. The incoming class looks healthy. In the past, you come in and you would be nuclear engineering undeclared, and they changed the process around. So everyone comes in, you can have an intent or you can remain undeclared. Of the group that has put down on their application nuclear engineering as an option, we're looking at last count, it was somewhere between 22 and 24. Now, there seems to be something going on. I think all of our press releases and sending that out through the university is helping, because I'm getting additional calls from students saying that they're interested in how do they switch to be a nuclear engineering intent. I suspect that when we get to new student orientation, I'll have a better idea as to the number that would be in that group, and then those that will we call it CODA, change of degree audit, will actually come into the department. And then there's a running note about us being in the NCAA Baseball World Series. Yes. Did I catch up with all the questions?
I've got one more question, if I may.
Sure.
Okay. In the introductions, as I recall, and maybe I'm not calling it correctly, but there was mention of a study on spent fuel storage. Did I hear that correctly?
Yeah, I can answer this actually, because we are very much interested in the fuel storage and the spent fuel storage.
Right.
So we do a lot of studies on computational studies on dry cask. We also study special coatings that will be coatings on the inner canister, as barriers and the multi-barriers. We do experiments. We investigate corrosion, and we do the necessary attenuation studies for the gamma ray if we have a special form of the the configuration for the canister. We also are very interested in concretes and the forms of concretes, as well as specialized glasses. And so we do a lot of related research to waste disposal.
Is this just domestically, or is this also internationally?
No, we do it here, not internationally, but in recent time, we were contacted by a group from Tunisia, that they have some special form of fine aggregate, and they asked us if they can send it to us, and so we can test. So they send us the mortars and the concrete samples, and we assessed, and we did the complete study, and we published it together in several journals.
So Caleb?
Yeah, Marshall, thank you. I just think it's super interesting that NC State is working with both X-Energy and TerraPower on their nuclear reactor projects. And this is to kind of echo a question put in the chat by Sven a little bit earlier. But could one of the panelists include a little bit more detail about the work being done with those companies?
So we're at the beginning stages of those two in way of signing the teaming agreements, and it is to move research a little more quickly so that then it can be brought in front of NRC. So we're trying to reduce the timing for that.
Yeah, yes, yes.
But still at the beginning stages in way of kind of the administrative components of things, with the goal of completing to get to NRC for licensing review. Stay tuned for more details as to the content of those two agreements.
Yeah, this is true because it's still in the beginning. So, you know, we cannot say that there is much that has been done. It's actually ongoing. And I know that Maria and Nam, you know, they are doing a lot of, you know, preparations and coordination.
And a related question, related to TerraPower and X-Energy, are there intellectual property issues with who can share what within the department?
I think yes, you know, there is, you know, and of course they sign agreements on these things, and it's a pretty, you know, a standard thing to do. You know, if you are working with companies, big companies like TerraPower and X-Energy, you should expect that, you know, there should be some intellectual property that has to be, you know, protected.
Richard?
Lisa, at the beginning of this presentation, did I hear you correctly state that these two projects, TerraPower and X-Energy, are commercial scale, and it's envisioned that they'll go online in 2027?
Not sure of the timeline. So whenever they're getting it to NRC, the idea is instead of 10 years to NRC, to reduce it to 7 years to NRC. So it's still a floating as to the licensing component of it.
So are you referring to 7 years as just to get through the licensing process?
Right. So
not the actual construction and going critical.
Right. So the idea is to reduce the review by 3 years.
Yeah.
Sven?
So I just want to add, I mean, I work on both those projects as well. And
Okay.
yeah, we are supposed to have those functional in 2027.
Yes.
Okay.
So, yeah, the licensing aspect is supposed to take about 3 years for the construction license, and then there's an operating license after that.
With that time frame, I do have a follow-up question then. When I got out of NC State in 1978, I worked the startup of TVA Sequoia plants, which were Westinghouse PWRs, gigawatt scale. It took a dozen years to put those plants online from the time they broke down. More than 40 years later, it's still taking Georgia Power more than a dozen years to put gigawatt scale Westinghouse PWRs online. In view of that experience in the nuclear industry and the difficulties they still have putting a plant online in less than a dozen years, do you think that 2027 timeframe is realistic for a new unproven technology?
It is a big wish. Of course, you know, 2027 would be great if it could be achieved. And I think that there is, you know, a grand challenge into it.
Steve? Oh, sorry, before Steve, June? Sorry, June?
Yes. Actually, I'm from South Korea now, and actually here is in the morning. But I have to go to work as soon. Before going to there, I came to here and I've got very nice information about nuclear fusion power and North Carolina State Department, nuclear department. And at last, I wondering this day if the U.S. government is willing to more invest in the nuclear fusion power. So,
are we going to invest in fission?
Yeah, the fusion power. The U.S. government willing to more invest in fusion power or not these days? Or
We are through the Department of Energy in particular,
Okay.
the Office of Nuclear Engineering.
Yes.
And then also private company partnerships as well.
Private company partnership.
Yes,
Yeah.
right.
Okay.
So we're trying to finish the AP 1000 and then there's research work at small modular reactors, micro reactors, et cetera. That typically for us in the US is a partnership with your national laboratories, with Department of Energy, so government organizations as well, and universities.
Okay, got it. Okay, thanks.
Steve, you had a question?
Yeah, Lisa, maybe a comment more than a question. There was some discussion about the 7-year time frame for getting the demonstration projects online, and I will say that certainly that's a very aggressive time frame, but I also want to remind folks here in the nuclear industry that this is what we have to do if we're going to be competitive in this clean energy sweepstakes that we're in. There's no mistake about it. We're not just out here and everybody has to come to us because we're nuclear. We're competing in this game. And if we can't get things done on a reasonable schedule and online, then we have no part of the clean energy future. So this is the time. This is nuclear's. We've got 2 strikes behind us, and we've got to deliver this time. So before you say it can't be done, what you need to say is, how can we get this done?
And Ryan, I see your hand.
Yeah, and just to echo Steve's point just a minute ago, nobody thought the Koreans could go to the Emirates and commission 4 plants in the span of, well, I think it's been around 10 years. So we certainly can't take the same approaches that we've taken in the past. But just to echo Steve's point, that's the environment that we're having to compete in. And as we've seen time and time again with engineers, when they sit down, knowing what the constraints are, we always seem to find a way to overcome challenges like timelines and licensing timelines have been adjusted and improved upon. And I have no doubt that our production and installation schedules can be refined and improved upon. So working our way forward, as Steve reiterated, this is the challenge we have to face. And there isn't a lot of wiggle room because there are other sources of power production that can be brought online in those timescales, and that's what the industry is demanding. So.
Wonderful. So, any last sets of questions? I'm mindful of our time, and we haven't seen the video. I'm going to put into the chat. There are 2 options. I put into the chat with the link to the longer video that we have. This was done for an IAEA workshop where we were hosting a session, and this was made for that, and it's longer than the one that I was going to show, but it incorporates everything in. And for those that want to stay and watch the video, I can play it as well. Your call.
Let's watch the video.
Let's watch the video then. I'm going to. Okay. be very slowly. Just have to move this away. All right.
My name is Ayman Hawari. I am Professor of Nuclear Engineering and Director of the Nuclear Reactor Program at North Carolina State University. We are standing here in the control room of the Pulsar reactor. The Pulsar is a 1 megawatt thermal power nuclear reactor facility. It was built in 1972 when critical at that time, and it's been in operation since then, almost 50 years of age for the Pulsar. The Pulsar is used for various activities, including supporting nuclear engineering classes, doing research using neutron and radiation beams, and also serving all kinds of users from the community and the industry, and also research organizations and government organizations by providing radiation facilities and radiation diagnostic facilities. What you see here is the control console of the Pulsar reactor. This is where our operators actually, on a day-to-day basis, monitor and operate the reactor, take it to different powers in order for the users to be given the type of radiation environments that they need and see. The Pulsar is a reactor that is fueled with uranium-235 fuel that is in a UO2 form and enriched to about 4% or 6% in U-235 weight ratio. Also, it is cooled by light water, moderated by light water, and it's an open pool reactor facility where the core sits in a light water pool about 25 feet depth. The reactor itself is somewhat unique in that the moderator to fuel ratio of this reactor is almost 1, which really gives us a neutron environment where the thermal neutrons actually peak on the edges of the core, facilitating the type of utilization that we do in the Pulsar. The reactor is controlled by different control rods, and we can see here on the console the indicators for these control rods. The rods are made out of an alloy of cadmium and silver and indium, and this allows the operators to manipulate the power of the reactor and to make it reach a certain operational condition. We have an actively cooled core in that we have water being pumped in the core in order to make the core always stay at safe temperatures. The reactor has a primary cooling system connected to a secondary cooling system, and then eventually the heat is released to the environment. The core has several irradiation locations, like these standing pipes, where we can insert samples and irradiate them for different purposes. We also have the ability to introduce samples quickly and swiftly and remove them from the core through a rabbit tube system that allows us to pneumatically move those samples in and out of the core. We're also able to build facilities around the core over here for irradiation purposes. This reactor is also flexible in utilization because we can, as I said, manipulate the working conditions of the core in order to demonstrate various aspects of reactor operations. To give you an idea of the different facilities that we have established around the core of the reactor, and as you can see, this is the core again with the tube structures that I have discussed. This is a view of all of these instruments. We have instruments that can do neutron scattering on samples in order to study the structure of these samples at the micro and nanoscales. We have instruments that can do neutron imaging and radiography in order to see the internals of larger samples and, for example, examine them for any kind of defects and damage. And we have an instrument that is quite unique that is able of generating positive electrons. These are the positrons that interact with the samples and give us an idea of the defect structure in these samples. Because many times when samples are manufactured, you might have actual atoms that are removed from their positions and have defects in the samples that control the properties of the sample. We are now building a new facility around our reactor, which specifically aims at testing advanced nuclear fuel materials, looking at microspheres of fuels And these microspheres then are studies in order to see how they behave under fission conditions. We also have a facility to look at fundamental nuclear physics aspects or neutron physics aspects. This is the ultra cold neutron facility, where we thermalize the neutrons to a very low energy at the nano electron volt scale. And then we are able to trap these neutrons and study their properties as free neutrons, such as the decay and lifetime of these neutrons. We are operating all these facilities simultaneously. Our staff scientists are able to operate, and also while other experiments and irradiations are taking place around the core itself. One of the unique capabilities that we have is the ability to use the educational aspects of our reactor through the internet. And we've introduced years ago the concept of the Internet Reactor Lab. In this capacity, the reactor console is rendered through a digital rendering and cast through the internet to students that are interested in understanding the operations of our reactor. In addition, those students are able to communicate with our operators through a video conferencing system. The console, as you can see it here, is rendered as a graphical user interface. And we also have graphical user interfaces for the different experiments that can be implemented through the Internet Reactor Lab. We are currently operating, and so all the readings that you see right now are actually real time. We have indicators of rod positions, powers, we have power meters, and we also have indicators related to our pool and temperatures. Through this capacity, we are able to introduce the students to various topics of reactor physics and operations. Experiments can be done to understand the criticality of the reactor and how to achieve critical conditions. Experiments can be done to understand the characteristics of the control rod by measurement of the rod worth of different control rods in the reactor. Experiments can also be done to understand the neutron field and the neutron flux distribution within the reactor core. And these are just examples of the various experiments that we can do. Working through the internet, we are able to share the capability of our reactor with different students around the country, different university campuses, and we've also developed the ability to do these internet lab exercises with the international community. And we actually implemented it and tested it in several countries. And in some cases, we offered it to students in those countries as coursework that was taken for academic credit. We've worked with the IAEA to develop this capability. And we've also transferred this ability so that the IAEA can develop it with other countries.
This is our nuclear simulation lab at the Department of Nuclear Engineering. In this lab, we have this generic PWR simulator, which we use for our curriculum and research and outreach. So this GPWR simulator is a numerical model that models all the way from the reactor core to the turbine with the primary loop, secondary loop, and the safety systems. So it is a very important supplement to the simulation capabilities that we have in our program. In terms of teaching, we have incorporated this simulation lab, our simulator, into our nuclear reactor laboratory course, where we worked together with not only the pulsar reactor, which is the research reactor we have on campus, but also this numerical, full plant nuclear reactor simulator. And so students can have a full, complete experience of operation in a commercial nuclear power plant. We have been heavily using this GPWR simulator on our research side as well. More specifically, we have been using the simulator to generate a large amount of data to demonstrate the operation of commercial nuclear power plant. And those data is valuable for us to develop and train any machine learning models that could help us to determine the unseen pattern in the data, which will then be very useful for us to perform prognosis and diagnosis of the nuclear reactor systems.
My name is Ryan Scholl. I am currently a postdoc here at North Carolina State University, working under Dr. Jamel Kayomi. I have recently transitioned from a PhD student to a postdoc, and I am able to work on a multitude of projects here. Basically, our research looks into the materials that are used inside the reactor as well as outside, and we want to understand how the effects of stress, corrosion, and irradiation are on the materials. We specifically look at the microstructure of these materials using electron microscopes over at the Analytical Instrument Facility on Centennial campus. And we basically want to understand how the microstructure changes, because the microstructure governs the macroscopic properties such as the tensile strength and the ductility. Here we have our tensile and polishing lab, and here to present some of our work is Chris McRoby.
Hello, my name is Chris McRoby. I am an undergraduate student here at NC State. Here we have our Instron tensile testing machine. I work with Dr. Kayomi on this machine. The machine utilizes DIC, digital image correlation, to take pictures of our samples. Our samples are marked with these speckled patterns, and what this allows us to do is look at these speckled patterns as time goes on and see a local strain map, examine how the strain changes with respect to time. We're currently working on a project with INL, Idaho National Laboratory, where we're examining anisotropic materials such as zirconium, graphite, and other HCP materials, establishing baseline mechanical properties. We then plan on irradiating the samples and examining how these tensile properties change under an irradiation environment.
Our project involves developing new nickel-based oxide dispersion strength nickel alloys for structural application and generation for nuclear reactors, specifically the molten salt reactor. ODS alloys are usually made out of steel, but we are trying to further develop their radiation resistance and corrosion resistance by using nickel as a base. This project is funded by the Department of Energy in collaboration with the Idaho National Laboratory, UC Berkeley, and Oxford University. So the nickel powder is mechanically processed at UC Berkeley. After that, here at NC State, we investigate the microstructure using electron microscopy, like TEM and SEM.
I have been working on thinning down some high entropy alloy samples of different chemical compositions to 100 micron and preparing them for transmission electron microscopy. Once these samples have been thinned down to 100 micron, we punch out 3mm discs from them, which are then electropolished until electron transparency, and then they are ready for transmission electron microscopy. These samples are then sent to the Argonne National Lab, where we use their IBEM microscope, which allows us to irradiate the samples with ions and allows us in situ to observe what is going on in the transmission electron microscope. This allows us to follow the microstructural evolutional changes in the alloys during irradiation. The goal of this project is to observe in high entropy alloys its radiation resistance in regard to its chemical composition and the elements involved and what role each element plays in assisting or not assisting the high entropy alloys in their radiation resistance. So we have been looking at a particular class of high entropy alloys in the refractory section containing elements such as zirconium, niobium, tantalum, vanadium, and molybdenum, along with another system containing iron, chromium, nickel, and manganese. These samples have been prepared for us by the Idaho National Lab, which we are working in collaboration with, along with Bowling Green State University in Ohio, which is also working on observing positron annihilation spectroscopy in these same alloy samples.
I'm participating in potassium hydroxide project, which we are thinking of using potassium hydroxide to replace lithium hydroxide in pressurized water reactors. Currently, nuclear industry use lithium hydroxide to control water chemistry in pressurized water reactors. The lithium here is not a natural lithium. It should be enriched to a specific concentration. However, the cost for procuring lithium-7 has been increased significantly since 2015. And the potassium hydroxide is considered as a candidate. since it's been used in Russian reactor for a long time. Also, potassium hydroxide doesn't need to be enriched, so it's economically favorable. Our collaborators include UC Berkeley, Pacific Northwest National Lab, and Electrical Power Research Institute. The objective of this work is to determine if it is possible to switch lithium hydroxide to potassium hydroxide without worsening the corrosion behavior of structural material in a reactor core. This is one of the sample we have. As you can see, it's very shiny because we did some sample preparation and we will put this sample on this tree. And we will flip this pad into the autoclave. And these two are static autoclave. They are very similar to real reactors, but just in a small scale. The temperature can go very high, around 325 degrees C, and the pressure is 2,500 PSI. And there are two autoclave, and because we want to separate different water chemistry solution. One would be lithium hydroxide, and the other is potassium hydroxide. And after exposing the sample into the autoclave for a certain time, the sample will be taken out. And we will do analysis such as TEM, SEM, or SIMS. We'll use electron microscope to observe what's the oxide formed on the materials. And we will use secondary ion mass spectrometry to study how the lithium or potassium cations penetrate into the oxide film to have better understanding for corrosion behavior in new water chemistry.
I'm here to present our recirculating loop autoclave, which allows us to simulate both boiling water reactor conditions and pressurized water conditions. And what we can do with this is actually monitor the water and chemistry at the same time as we're running our tests. We can add various dissolved chemicals such as lithium hydroxide, potassium hydroxide, or boric acid, as well as gaseous species, for example, such as hydrogen, to hydrogenate the water as you would see in a pressurized water condition. The other interesting feature of our loop autoclave that we have here is it also has a tensile machine attached to it, which allows us to add stress to our samples while we're running our tests. And that would be known as a stress corrosion cracking experiment. With that, we have a direct current potential drop system, which allows us to measure the potential drop over the course of the time and being able to relate that to the crack length so that we can actually get something like the crack growth rate, which is an important parameter. One of the projects that is associated with this is known as the silicon carbide project. Ever since Fukushima happened, we are always looking for accident tolerant cladding. And one of the cladding candidates that we have is silicon carbide. The problem with silicon carbide is it corrodes a little faster than we like in boiling water conditions. So what we're looking to do is add on a coating either by physical vapor deposition or chemical vapor deposition, such as titanium nitride or zirconium nitride. And that project is just looking to see how fast our material corrodes and if we can improve it. So here we have one of our tensile apparatuses that actually allows us to do some in situ stress corrosion cracking over at Argonne National Lab's synchrotron source, which is known as the Advanced Photon Source. This project specifically was looking at canisters that we use for our spent nuclear fuel. And the problem with it is you could get a risk of crack propagation via chlorine-induced stress corrosion cracking for the canisters that are near the coastal of the United States. So what we were able to do is actually take cracked samples that we already pre-cracked and actually add in some salt and add some stress to it so that when we take it to Argonne National Lab, we can actually run our test and take what's known as X-ray tomographies over the course of the experiment. And what that allows us to do is basically track how far the crack is going and also the shape, which are both very important parameters.
Plasmas are used a lot for microelectronics manufacturing and for materials processing. And so we were doing a lot of work with companies like Samsung or Micron. We were doing work to basically make sure that you could make smaller and faster computer chips. And since that time, we've gone through this really fascinating transformation in our department as far as plasma science goes, where we continue to focus on our core knowledge base, which is still the materials processing and manufacturing, but have since then also moved into new areas. In fact, right now is plasmas for life sciences, using plasmas for things like medical treatments or treating biological materials. Professor Stoppelman is leading a multidisciplinary effort to use plasmas, among other technologies, for advanced agricultural applications, such as fertilizer production. So there is a ton of really exciting things that we would have dreamed of 10 years ago that's going on right now. And then, of course, along with all that, we also have our collaborations with national labs where we do more of our traditional fusion energy work. So we worked with Oak Ridge National Labs developing diagnostics for some of the monitoring plasma heating devices that they use for tokamaks. We were working with INL on expanding computational frameworks so we can do simulation work for fusion reactors. So there's lots of exciting things we're doing right now. So a bit of a catch-all, but definitely have our areas of expertise as well. First thing I want to make sure is I want to say that, I'm obviously speaking on behalf of myself and also Professor Katarina Stoppelman, who's the other faculty member who works in the plasma lab. And also we have Dr. Alexander Vitaler, who, although he doesn't have any experiments in this facility, his experiments are upstairs on the second and third floor. He's also collaborates with us quite a bit on plasma projects. He works a lot with ultrafast spectroscopy and ultrafast lasers. So the students you'll be seeing today, first one is Nick Sponsel, who will talk a little bit about some of the work that's going on here in the Plasma Life Sciences Lab. We also have Carl Smith, who's doing some work funded by Samsung Electronics, trying to develop advanced plasma sources and advanced plasma technologies for microelectronics manufacturing. We have Josh Morsel, who's a graduate student working as part of a Department of Energy center that we're part of, where we're studying plasma interaction with complex interfaces. So broadly in the center, we focus on plasma interactions with nanoscale materials, plasma enhanced catalysis, plasma interaction with liquids, which also has obviously a lot of overlap with some of the stuff that Professor Stoppelman's doing. So he's the graduate student who's supported through that center. And then finally, Naaman Bhatt, who's working on a project supported by a startup company here in the Triangle, Terra Medica. And we are developing plasma processes to purify chitosan powder for a host of medical applications. Everything from removal of toxins in biological systems to pharmaceutical drug delivery. So our role in it is actually taking the powder and purifying it to a level where you can use it for internal medicine, which is kind of exciting. We should be able to show over the course of this, also have some really nice demonstrations of some of the experiments that we're doing here as well.
So thank you so much for staying to the very end. I hope that the video was a nice ending, a nice highlight to.
It was fascinating.
Wonderful. Randy, do you want to close us out or?
Yes, I will. Lisa, thank you very much. Dr. Bourham, Dr. Trivedi. Again, you guys shared your time tonight with us. Excellent presentation. I had no idea that you guys were doing all that you're doing. And it brings back memories of 1970 when I took intro to nuclear engineering when I was at State. A lot's changed since then. So anyway, you guys are doing a great job. And thank you very much. Now, you had mentioned recording. Is this going to be posted?
Yes.
Where people who could not participate tonight would be able to see it?
Exactly. So what I will do, I know the system will take a little bit of time and then it'll send me an email and I will post it on our NC State Nuclear YouTube channel and I'll also get you a copy.
Okay, if you please. And also, could we get a copy of the slides?
Yes, indeed. I'll send that too.
Okay, that would be great. Okay, well, that's pretty well wraps up the meeting. Just very briefly, from an ASME point of view, this wraps up our 2020 to 2021 fiscal year. It ends the end of the month. And so we will be starting anew next year. We're sending out a hard copy newsletter to our membership. Please provide feedback so that we can be the kind of ASME section you'd like for us to be next year. Ryan, would you like to say anything about ANS?
Yeah, this also will be the last technical session that ANS is going to have for the year. We are doing a no-host social on the 15th of July at Old Mecklenburg. So anybody is welcome to attend if they'd like. I've been doing lots of research to make sure that there's going to be plenty of room at Old Mecklenburg at various times of the day, various days of the week. So I encourage everyone to further that research ahead of the 15th, and then join us on the 15th if you'd like to. And then I do look forward to doing some more joint things, and certainly becoming more involved with NC State, all the things that are going on there that we can work collaborative on to help further the nuclear and the ASME causes. So thank you.
All right, thank you very much.
Thank you. Have a wonderful night, everyone.
Yes, thank you. Thanks everybody for attending. All right, bye-bye.
Bye-bye.
Thank you.
You're welcome.